Neutron stars are some of the universe's most fascinating and mysterious objects. They form from the remnants of massive stars that die in supernova explosions, powerful blasts that mark the end of a star's life. When a star, with a mass much greater than our sun, runs out of fuel, it collapses under its own gravity, creating an explosion that ejects its outer layers into space. What remains is a core so dense that it becomes a neutron star. These neutron stars are incredibly compact, so dense that a single teaspoon of neutron star material would weigh as much as a mountain on Earth. But neutron stars aren't just interesting because of their density. They hold clues to some of the deepest mysteries in physics and astronomy. When two neutron stars collide, they release huge amounts of energy and create gravitational waves and ripples in the fabric of space-time. Observing these collisions can help scientists unlock secrets about the universe's beginnings, its forces, and even its future. The life of a star begins with a process called nuclear fusion, which takes place in its core. In this process, hydrogen atoms combine to form helium, releasing tremendous energy in the form of light and heat. This energy pushes outward, balancing the inward pull of gravity and allowing the star to shine steadily for millions or even billions of years. But eventually, a massive star runs out of hydrogen fuel, which changes everything. When the core has no more hydrogen to burn, it begins to fuse helium instead. This process releases energy, but not as much, causing the star to expand and transform into a red supergiant. In this stage, the star's outer layers swell up, making it many times larger than its original size. The final phase is the most dramatic, the supernova. When the star exhausts its helium, it no longer has the outward pressure needed to counter gravity. As a result, the core collapses rapidly, crushing itself inward. In less than a second, the core, once the size of Earth, shrinks down to just a few miles across. This sudden compression causes a powerful shockwave, which blasts the star's outer layers into space in a brilliant explosion, sometimes brighter than an entire galaxy. The supernova leaves behind a dense core, which becomes the neutron star. Neutron stars are among the smallest but densest objects in the cosmos. Despite their small size, typically around 20 kilometers in diameter, they pack more mass than our sun. You can just imagine it, like taking all that mass and squeezing it into a space no larger than a city. The result is a material so compact that a piece the size of a sugar cube would weigh as much as a mountain. Neutron stars also have incredibly strong magnetic fields that's trillions of times stronger than the Earth's magnetic field. This intense magnetism often creates powerful beams of radiation that shoot out from the star's magnetic poles. When combined with their rapid spin, which can be as fast as hundreds of rotations per second, neutron stars become some of the most extreme objects in the universe. Inside neutron stars, matter's packed more tightly than anywhere else in the universe. The outermost layer, or crust, is a thin, incredibly strong shell made of atomic nuclei surrounded by free electrons. Below this crust lies a denser region where the matter forms strange shapes, resembling lasagna or spaghetti. Scientists call this layer nuclear pasta. Beneath the nuclear pasta layer, in the core, conditions become so extreme that scientists believe atoms break down entirely, leaving only neutrons or even quarks, the fundamental building blocks of particles. Neutron stars come in many forms, but one of the most fascinating types is the pulsar. Pulsars are neutron stars that emit steady, rhythmic beams of radiation, often in the form of radio waves, light, or even X-rays. These beams sweep across space like the light from a cosmic lighthouse. Every time the beam points towards Earth, we see a pulse of radiation, which is why they're called pulsars. When a massive star ends its life in a supernova explosion, it can leave behind a rapidly spinning neutron star. If this neutron star has a strong magnetic field and is spinning at just the right angle, it becomes a pulsar. As the neutron star collapses during the supernova, it shrinks down to a very small, incredibly dense object, conserving its angular momentum. This means it starts spinning faster, much like a figure skater who spins more quickly by pulling in their arms. The magnetic field of a pulsar is incredibly strong. This field channels particles and energy to the star's magnetic poles, where they're blasted out as beams of radiation. Because the neutron star spins, these beams sweep across space. If Earth happens to be in the path of one of these beams, we see it as a regular pulse of radiation. One of the most amazing things about pulsars is their regularity. Some pulsars rotate hundreds of times each second, and their pulses are so steady that they rival the accuracy of atomic clocks. This precision makes pulsars incredibly valuable to scientists. By carefully tracking the timing of these pulses, scientists can use pulsars to study everything from gravitational waves to the conditions of space itself. For example, when two neutron stars orbit close to each other and create ripples in space-time, the timing of the pulses from a nearby pulsar can change slightly. By observing these changes, scientists can listen to the gravitational waves and learn more about them. Pulsars are also fantastic tools for testing theories like Einstein's theory of relativity. Since they're affected by the intense gravity around them, we can study these effects in the pulses they emit. Observing these effects has already helped scientists confirm several of Einstein's predictions. Not all neutron stars wander alone through space. Some exist in pairs, called binary neutron star systems. When two neutron stars are bound together by gravity, they orbit around each other, creating one of the most energetic and intriguing setups in the cosmos. When neutron stars are in a binary system, they can sometimes interact with each other in extreme ways. If one star is pulling material from its companion, this is called mass transfer. During mass transfer, matter flows from one neutron star to the other, changing the way each star behaves. Mass transfer can make one or both stars spin faster and can even lead to explosive events, where energy and radiation burst out in all directions. In some cases, if the mass transfer goes on long enough, it can cause one of the neutron stars to collapse further, possibly forming a black hole. In some binary systems, the neutron stars may orbit so closely that they start to spiral toward each other. Over time, they get closer and closer until they eventually collide. This collision becomes a powerful event called a kilonova, where the energy released can outshine entire galaxies. Kilonovas are also important for element creation. The extreme conditions during a collision allow for the formation of heavy elements like gold and platinum. When two neutron stars orbit each other, they don't just affect each other. They also send out gravitational waves. These waves are like ripples in space-time, spreading out from the orbiting pair and carrying energy away. Because of these waves, the neutron stars gradually lose energy, drawing them closer together over time. Gravitational waves were first predicted by Albert Einstein in his theory of general relativity. For many years, they were only a theory, but in 2017, scientists directly detected gravitational waves from a neutron star collision for the first time. This discovery confirmed Einstein's prediction and opened up a whole new way of studying the universe. Observing gravitational waves from binary neutron stars helps scientists understand the nature of gravity itself, along with the incredible physics of neutron star collisions. Neutron stars have powerful gravitational fields, so when they move through space, they can have significant effects on nearby objects, like planets and clouds of gas and dust, known as the Interstellar Medium. The intense gravity of a neutron star can disturb planets that happen to orbit nearby, stripping away their atmospheres or even pulling them apart if they get too close. The strong magnetic fields of neutron stars can also interact with the interstellar medium. As a neutron star moves through the gas and dust between stars, it can create shock waves that heat and compress the material around it. This can produce unique patterns of radiation and help scientists study the composition of interstellar matter. In some cases, neutron stars in binary systems can even trigger new stars to form by compressing clouds of gas they move through space. Interestingly, some neutron stars have planets orbiting around them. These exoplanets are usually formed from the leftover material after a supernova explosion, which gathers into clumps and eventually forms new planets. Studying these unusual exoplanets can give scientists insights into how planets can survive in extreme environments and how they might behave around such powerful objects. Although these planets would be exposed to intense radiation and gravitational forces, they're a fascinating example of the resilience of planetary formation. One of the most exciting things about kilonovas is that they create conditions for the formation of heavy elements. During the explosion, neutrons slam into atoms at incredible speeds, building up atoms of heavy elements through a process called rapid neutron capture, or the R process. This process creates elements like gold, platinum, and uranium, which are then scattered into space. Over time, these elements can become part of new stars, planets, and even the materials we use on Earth. In this way, kilonovas contribute to the cosmic cycle of matter, helping create the ingredients that make up our world. Kilonovas allow scientists to study some of the most extreme conditions in the universe. By observing these events, they can learn more about how heavy elements are formed and gain a deeper understanding of the processes that occur in star collisions. Kilonovas are also essential for the study of gravitational waves, which have opened a new way of observing and understanding space. Since gravitational waves travel differently from light, studying them provides a unique perspective on how events unfold in the cosmos. Researchers hope that future studies of neutron stars will reveal more about the nature of matter in its densest state. One big question is what exactly happens at the core of a neutron star, where matter is packed together so tightly that even atomic nuclei are squeezed into new forms. Scientists want to understand if exotic particles or strange states of matter, such as quarks or even strange matter, exist there, which could change our understanding of particle physics. Another key goal is to understand the role of neutron stars in the universe's evolution. Since neutron stars emit gravitational waves and contribute to element formation, studying them can offer clues about how the universe has changed over billions of years. By mapping neutron stars and their collisions, scientists can also gather data that may help explain how the universe is expanding and what drives its accelerating growth. Let us know your thoughts about neutron stars in the comments below. And if you're interested to know more about space, don't forget to watch our video on what did we learn from the first real pictures of Mercury. See you again. Bye.